practice with simplifying trig expressions. Let's do it. I've got a bunch of different examples up here. And again, trying to use lots of different tools to do this. Just replacing statements with equivalents, maybe converting everything over to sine, cosine, and tangent, maybe even converting all your tangents and cotangents over to just sines and cosines. Sometimes you can convert everything over. If you've got a numerator and a fraction that's got a sum or a difference, breaking up that fraction into two parts. If you've got two separate fractions being added, adding them together with common denominators. Again, factoring out a GCF is something you can do. Lots of different strategies here that we can possibly see in these problems. So let's see what we've got. First one here, I want to simplify. I notice I've got a cosine as both of these statements. So I'm going to factor out the greatest common factor and see if writing it in a different form allows me some additional insight. So cosine comes out. If I divide this by cosine, I get a 1. If I divide this by cosine, I'm left with just a sine squared of x. Remember that if sine squared of x plus cosine squared of x is equal to 1, I could subtract sine squared from both sides of this statement and find out that cosine squared is equal to 1 minus sine squared of x. And so I'm going to replace 1 minus sine squared of x with a cosine squared of x. Okay? And if I do that, we're going to find out here we have a cosine squared of x times a cosine of x, and that is going to leave me with a cosine of x cubed. If I can write it. All right, on to number 2. Okay, this one here, I see that I've got, I don't have secant squareds or cosine squareds or anything like that, so I can't use the Pythagorean identities. But I am noticing that a secant could divide into a secant if I could break this up into a form where there wasn't addition or subtraction in the fraction. So this is one where I'm going to break up this numerator, okay? But remember, if you break up a numerator, you've got to have it over the same denominator. So I'm going to do a secant of x over x plus a cosine of x over a secant of x. And we'll see what we can do there. So that's secant of x over secant of x plus cosine of x over secant of x, okay? So common denominator, we add our numerators, same statement, just written in a different form. That's 1, okay? Secant is the same thing as 1 over cosine. So I'm going to break this up a little bit differently. I'm going to rewrite this as cosine times 1 over secant of x. I'm basically factoring out. So as everybody see, this is still a cosine over a secant. But then I can flip that secant. That shows me that secant's reciprocal is basically going to go up into the numerator. 1 over secant is the same thing as cosine. Okay? So we got 1 plus cosine squared of x. Okay? Looks a lot like sine squared plus cosine squared equals 1, but it's not a 1 minus cosine squared, so I don't know if that was a mistake in the original problem, but anyway, we still got this down to a single trig expression, so that's pretty simplified. Okay, sine of x, cotangent of x, this time because everything's being multiplied. My thought is if I replace the cotangent with a cosine over a sine, then I can get some nice cancellation here. So cotangent, same thing as cosine of x over sine of x, and of course if we're multiplying here, we don't have to worry about common denominators or anything like that. We can divide a sine out of the top and a sine out of the bottom. We're going to get a cosine of x over 1, which of course is just the same thing as cosine of x. Nice problem. All right, on to the next one here. 1 minus sine squared. I could break the numerator up here. I could do 1 over cosine, and I could do a sine squared over a cosine. However, I know that 1 minus sine squared, actually from this problem back here, is the same thing as cosine squared. And if I write it as a cosine squared of x, then suddenly I can divide a cosine out of the top and a cosine out of the bottom, and that's going to leave me with a cosine of x over 1, which again is just cosine of x. So real original choices here, every problem having cosines in it. All right, this one, very much like number 1, I see that I have some sines in common. I'm going to factor those out. So sine of t times, it'll be 1 minus cosine squared of t. 1 minus sine squared is equal to cosine squared. Sine squared is equal to 1 minus cosine squared, if you go back to that original Pythagorean identity. So this is the same thing as sine squared of t times the sine of t should be equal to a sine cubed of t. And if you've noticed there, that's basically just the backwards version of number 1. Just flip the trig functions there, okay? And the last one out of the problems that I currently have on the board, I'm going to group this a little bit differently here. Let me see if I can get this on the screen. Hang on just a second. Yeah, I can fit that in. This is all being multiplied. So I'm going to kind of group things conveniently. I'm going to do a sine squared. This is called a beta, by the way, if you didn't know your Greek letters. I think I'm going to do a sine squared of beta. You know what? I'm going to break this up as a sine of beta times a sine of beta times a cotangent of beta. That's what's on the top. On the bottom, we just have a cosine of beta. So I'm going to do this as a sine of beta times a sine of beta over a cosine of beta times a cotangent of beta, okay? And so as everybody see, if I multiply across the top, that's the same thing that I have here. Bottom didn't change. I'm going to convert everything into sines and cosines here, which is always a really good strategy. This is cosine over sine, okay? So cosine of beta over sine of beta. And check out all the cancellations I get. Again, this is all a product, so it's still sine of square root of b, cosine of b over cosine sine of b. All of that, you know, could be written that way. So my numerator's got a cosine and my denominator's got a cosine. I can divide the top and bottom. And again, if this was addition or subtraction, it's a lot more complicated. But if it's all multiplication division, we can just divide the top and the bottom by the same thing. I can divide a sine of b out of the top and the bottom. And that's going to leave me with just a sine of b over 1, which of course is sine of beta, I guess, is technically what that is. And I've got 2 additional problems, so I thought, hey, let's go ahead and do those extra problems too. Let's see what's going on with those. All right, so question number 7. Question number 7 wants me to simplify the cosecant of b, cosecant of beta, we're doing a lot of betas now, over 1 plus cotangent squared of beta. And the final question in this set wants me to do a 1 minus sine of x times a 1 plus sine of x. Okay, so let's take a look at this top one here. By the way, anytime I see these squared terms, I think about the Pythagorean identities. And if you remember, 1 plus cotangent squared of an angle is equal to the cosecant squared. And that's very compatible with this. So let's go with our Pythagorean identities here. We can divide a cosecant of b out of the top and the bottom. That leaves me with 1 on top. Leaves me with a cosecant of beta on the bottom. Remember, the reciprocal of cosecant, we can write this a little bit more neatly, is sine of beta, and we're done. Okay, last one. We've got parentheses here. Let's FOIL this out and see what we get. So 1 plus sine of x minus sine of x minus sine of x times sine of x, which is sine squared of x. Okay, notice it's a difference of squares pattern. Like differences of squares, we get those middle terms that cancel. I get a 1 minus sine squared of x. And remember that 1 minus sine squared of x is equal to the cosine squared of x. And so that's been pretty common. We've seen a lot of denominators, common denominators for that kind of thing. So hopefully that's not too shocking to you. Hope those examples helped.